Okay, guys. So what did we cover last time? We said, if you remember, we did heaps, correct? And why did we even explain heaps? To solve what? What was the issue? What do you think, Melanie? When do you think we actually arrived to the idea of heaps? We were trying to solve what? Priority queue, very good. So technically, we had the ADT of priority queue and we implemented with sorted, unsorted sequence. And what was the problem that we faced with the sorted and the sequence idea? Because we actually faced a problem or an issue that led us to do the heaps. What was the issue that we faced? Implementing the priority queue with sequence, with like a list. What was the issue? Yes. Exactly. So the sorting was one of the problems, but the whole idea is that this one is linear. The sequence, the list is linear. If I want to go to search or to do something to add, I have to do it linear. And what is linear? Big O of what? Big O of n. We said, okay, can we do something better? We said yes. So that's why we start using the heap to implement the priority queue idea. And heap is based on what? Why it's better? Riley.
Based on binary trees, accessing elements in size.
Very good. So it's based on binary tree, and more specifically, it's based on what? What type of binary tree? Complete binary tree. Because with complete binary tree, we're able to keep the height log of n. And then if we keep the height log of n, then we're able to have a better efficiency. I think it was very understood. Everyone got the idea. And then there was a small unclear thing, which was what? The down heap versus the up heap. You remember? And when we did the WOOC lab at the end, half of the class was still confused. So I create these slides, extra slides. They are in Brightspace. You can check it. And we're going to go through it a bit. And then we will cover HeapSort. And we will move to our new topic. So we have up heap and down heap, correct? Okay, so what is up heap? Up heap is when we add something to the tree. The whole idea with the up heap, because I'm adding, so let's say I have this tree, and I added something here. So I added something here. The up heap is that we only compare with the parent. That's it. I do one comparison with the parent and then go upward. Okay. This is opposed to what? To something called down heap. Down heap, we're always looking at the root. So we're always looking at the parent. So that means how many comparisons I need to do in this case? 2. Why 2? Because each parent will have 2 children at most. So sometimes you're going to do only one comparison. But let's say you're going to have, so you're looking here now. So you can have up to 2 comparisons. Why do you want to compare? Because let's say you want to choose the minimum or the maximum. So what is the main idea between up heap and deep heap? Up heap, we're only comparing with the parent. Down heap, we are the root and comparing with both children. Okay? So up heap and down heap has nothing to do with max heap and min heap. It's not like the down heap is reserved to min heap and the up heap is reserved to the max heap. No, we can apply both to min heap and max heap. So let's take an example. The example of down heap, we said, why we're comparing twice? Who can tell me? Yes.
Complete binary tree, so we can check for board children.
Yes. So why 2 comparison, not one? So where are the comparison? Let's say I'm here. So where are the comparison between what node and what node? So one comparison here and one comparison here. That's what you're saying. Okay. Different answer? Yes. The one behind you. Yeah.
Both children, and then whichever one is both dependent, you're doing max heap and min heap, and then you compare to the.
Okay. Thank you. You had the same answer?
Yeah.
Okay. So technically there is two ways. Both of them are logic. So it's either you are comparing this with this and then this with that, or you can just compare the left with the right. So I'm going to say 4 is less than 6. That means my minimum child is on the left, and then I'll compare 20 with this left. Okay, so the algorithm that's written for us in the slides in the book is this way. So we compare the children's first, so that's the first comparison, and then we're going to compare this with the parent. Okay, but both methods are still two comparisons. But if I'm not mistaken, this one that is in the book, it's more efficient. So if you try it in the lab, you're going to know why it's more efficient. But I think this one is more general. It will cover more things, so more efficient. Anyway, so the idea here that we have two, a comparison, and then with the upheap, what do I have? This is I added 6. So I only compare it with the parent, and I go upwards. So that's the main difference first. So let's take a look. So now I want to do a heap construction. How many ways do I have when I want to construct a heap? We have only one way, 2 ways, 3 ways. What do you? 2? What are the 2?
I just remember there was 2. I don't remember the difference.
Okay, no problem. At least the first step is covered that we have 2 ways. Yes? Okay, so one of them is bottom-up construction, and the second one is what, James? Which is normal insertions. I'm just inserting from top to bottom. What is the difference between the two? And which one is better? Yes. Bottom up is better. Why?
Just check. Can you keep going up instead of checking twice?
No. Okay, so now you're confusing which one is better, down heap or up heap. We're still so far, and these both, so you're right, but this is inside the bottom up heap construction. Here I'm saying there is 2 ways to even construct the whole thing. It's either the normal insertion or the bottom up heap construction. So the next question will be this one that I'm going to ask you. So now I'm saying I have a sequence of numbers. I want to construct a heap first. So I want to construct the heap. I have 2 ways. It's either just normal insertions, one by one, or something called bottom up heap construction. Which one is better and why? Abed.
Bottom up,
Why?
complexity took only log n, but
The insertion.
the insertion took on
ON?
insertion.
Yeah, Curly. And so you're right, but the insertion will take n log n. Okay, so very good. So the idea is what? We said each time I want to insert something in the heap. So look at this one. I inserted this 6, correct? Is this done? Is this a min heap? Is this, sorry, a min heap? No. So each insertion I need to do, I need to also do the up heap, correct? So each insertion will cost me what? Maximum of log of n. Now, if I want to insert all of these numbers, if I have an empty heap and I start inserting, so that's my 3, that's 4, that's 7. So I'm going to do log n times n. So I'm going to do log n insertions n times. So I'll end up with n log n. We said this is not good. We need to find a way where we can keep the construction of n. That's why we said the bottom-up heap construction, which is this one, is better approach because it actually keep it O of n. Now, inside this bottom-up heap construction, we said we're going to divide it into mini heaps. So each one of these will be treated as mini heaps. Now we'll come back to your comment, and we said, when I'm treating this as mini heap, do I use up heap or down heap here? So what now answer? Up heap. Up heap here contradicts with your comment. Your answer before you said we need to start from up. What did you say last time? Because we have to compare twice and once. What did you say?
Up, we only compare one.
Yes. Okay, no problem. We'll go more steps. So guys, we said we're going to treat this and then this, we'll fix this and then fix this, fix this. So we'll fix the mini heaps until we get the min heap or the max heap, okay? So let's look at this example. I'm doing the construction bottom up heap construction of a min heap. Okay, guys, so let's look at this one here. I want to try the upheap. Is this a, because I'm treating each of these three nodes as a mini heap. Is this a min heap? No. So I'm going to choose the method to fix this min heap. What's going to happen? I'll start with 20. So 20, I do one comparison, correct? So I'm comparing it with 27. 20 is less than 27, so I'll end up with what? 20 here, and then 27 here. Is this a min heap? No. So I need to do another upheap here. So now this is going to be 19, this is going to be 20. So it took me, forget about the comparisons, it took me 2 actions, 2 executions to be able to complete this. Correct? This is the upheap. If I do this, 20 is still greater, so I'm going to do it again. Now let's try the downheap. I want to do downheap. What do I do? First, I compare these two. Which one is less? 19 is less, so I'm going to change it with the 27. Is this a min heap? 27. I'm done. So it took me only one action. That's why we're going, yes. No, one action. So the comparison is going to be twice, but I mean actions, executions, swapping. Because even here, you're going to end up comparing more than one, right? So if I look here, the first time you did this, there is one action, but also one comparison here, another action, another comparison. So you ended up with, let's say, 2 comparisons and 2 actions. There, you're going to end up 1 action, 2 comparison, for example. Yes, Ant.
So based on what I'm understanding, there's really like, you can't go wrong with using downheap because it always works.
Exactly.
So sometimes, in some cases, you don't have to check for like the right or left elements because we already confirmed that it's in the heap form. So we save just like slightly with the upheap.
Very good. So that's the whole idea. Well, it will work with both. But why would you, in the worst case scenario, take, for example, let's assume that it takes n. One of them is taking 2n, the other one is taking n. Why would you choose the 2n if you have the options to do it with n? Okay, guys, so again, the idea here is that with the downheap, we're only doing it once. So, and also why it makes sense, because if we're treating this, this as a mini heap, that means I have a root here. Whenever I have a root, I can compare with both children. So that's going to be fine. So what would be the next step? Who wants to do this other mini heap? What should I do here in this second one? James?
Swap 6 and 11.
Exactly. I'm going to swap 6 here, 11 here. Is this a min heap? Yes. So what would be my next step? Check this one. Is this a min heap? No. I'm going to get the 4 here, 5 here, and then I'll go here. So what's going to happen in this case? 15 and 25. So as you can see, okay. Now, someone may ask me, would this only work with the min heap? That's why I'm using down heap, or no? Even if I have a max heap, it's going to be the same thing. Let's try this. We have a max heap here, and I want to use the down heap. Would it work? So is this a max heap? Yes, I'm not going to touch it. Is this a max heap? Yes. Is this a max heap? No. So I'll switch 5 by 12. Is this a max heap? Yes. So this is done. Now I go here. I'm checking all of this together. And then I'll need to check if it's a max heap. I go here. I switch these two. And then another check here. All of them, I'm doing down heap. Because why? Because if I'm checking all of this, I have a root. I'm always going to start with the root and start going down. It has nothing to do with maximum min heap. So I think it's clear now. Any question about this? So you can go through this slowly at home. Let me check if there's anything. Yeah, so there's no other. Yeah. Yes.
Make sure the plexities square and n square.
It's not n square. According to the slides, if you go back, we're going to end up with O of n for bottom-up heap construction, compared to n log n with the normal construction. Okay. Now in the tutorial, if you didn't watch it yet, we're going to cover both. We tried both, right? The bottom-up heap construction and the normal construction. We can compare them. Now let's go to which one? I think we need to continue the HeapSort. Okay, so if you remember, we stopped. We stopped here. Okay, so now again, the priority queue, we tried to implement it within the sequence with a list, but then we said we can use the priority queue to sort, if you remember. And we use the ordered or unordered sequence to sort correct. And then we did selection sort, insertion sort examples. Now I can do the same thing using a heap and sort them by something called HeapSort. What is the idea of a HeapSort? I need to do two things. Build the heap first, because I don't have a heap. I have a sequence of numbers. I have a list. I have whatever. I want to sort this. So I need to build the heap first and then do what from the heap, similar to what I did with the ordered sequence. We call the remove min or remove max. So we want to just call the priority one. So it's going to be covered. Now, this is the algorithm for priority queue sort. So what we did here is just we have this S that has the numbers that I want to sort. And I'm going to say, after I remove first from this list and insert it here, I save it here, and then I'm going to insert here. Okay, so let's take a look. The construction of the initial heap will take O of n. Why? Because I want the best efficiency, so I'm going to choose the bottom-up heap construction. If I'm using bottom-up heap construction, it will cost me O of n. So that's my first cost. Now, what else? Each time I'm sorting, I need to call the remove, correct? Okay, so it's going to cost me O of 1. Then I need to rearrange. The rearrange is what? Log of n. Okay, so who can tell me what is this? We already covered it last time. How do I calculate this? Because I have here n minus 1. So it's just a summation of this, correct? So it's going to be what? The summation of the logs from 1 to n. I'm going to end up with n log n. So the heap sort will cost me n log n. Okay, guys? The heap sort will cost me n log n. And this is matched with the merge sort, quick sort. So we can never have anything we don't have, like so far, unless someone comes up with this. Any sorting algorithm that is better than n log n. We don't have it so far. Hopefully you graduate, you'll do your PhD, and you'll solve this problem. Okay, so we said in the sorting with the sentence, we said we can do it in place. What do we mean by in place? You don't have to create two arrays, right, to sort it. From the same array, we can sort it, if you remember. Now, with the heap sort, we can do the same thing. Let's see why. Guys, if I'm doing this, if I have 7, 10, 20, I have 13 and 15. Usually, if I remove min, what's going to happen? Who can tell me? There's no energy today in the class, huh? So if I want to do remove min, Joel,
Remove the top one?
I said remove min. What do we think?
This is the top one.
Exactly, because there's a min heap.
You remove 7, everything would go up by 1. For example, 10 would go to the top. And
Which course is this?
wait,
No, think about it a bit. So there has to be a procedure. So I remove 7. So I remove 7. It's empty.
last key. So
Exactly, very good. So I take the last key here, I delete it from here, I put 15, and then I do the down heap, correct? Okay, so what's happening now? I removed min, I'm storing it in a new place. I'm returning it to a new place. So if I'm sorting, I did remove min, now what's going to happen? I'll do the down heap, so the down heap will be what? We'll go 15 here, and then 10 here, and then we'll go again here. We'll have 13, and then 15, correct? Okay, I'll do another remove min. I'll take the 10 here, and then replace it with the 13, correct? Okay, so now technically I'm sorting them ascending order, but I'm not doing it in place. So how can I do it in place? Let's see. So in place, I remove the max. This is a max heap. I remove the max. I don't just put it somewhere and take the last element. I just swap it with the last element. So I'll keep it in the array here. Okay, I just swapped it. Then I'll continue. Is this a max heap now? It's not, so I need to do it. Where should I go, 20 or 19? Of course, 20. So let's do it. So I do 20, I switch it with the 20, and then is this a max heap? Now, if I tell you after your first down heap, how does it look in the array? Can you tell me now? Riley,
You can do, it would be like 20, 19, 7.
so because you're saying this is the index, I do this, so you're going to say it's going to be 20, 19, what, 7?
And I think 15, 15, 14, 11,
Okay,
and all the way across.
okay. This is after your first down heap. Anyone has different answer? So this is very important. So please, everyone focus with me. This is not a complete down heap. When I tell you do a down heap, you need to keep doing the down heap until it is a max heap again. So this is not a full down heap. Okay, so that means, no, you're going to continue transforming this to a max heap, then you're going to tell me how it's going to look. So,
Okay.
so in this case, you're going to continue here. So that's the 7. This is the 14. Is this a max heap? No, that's 8. That's 7. Now you're going to print 20, 19, 14 in this array, etc. That's now, so because this is going to, if you look at the tutorial, we're going to always ask you this. For example, after your first down heap, or I'm going to tell you not after your first down heap, I'm going to tell you after your first remove max. You can't just switch it like this and you said, I removed max. You didn't remove max yet, because inside the function of remove max, we say we remove max and we do a down heap. All of this are considered remove max. Is this clear? Right.
It's still not a max heap, because your 22 is probably just.
Yes, because this is heap and sort. This is going to be treated as if it's outside the heap. So that's why I had it like this. This sort in place. That's different case.
It's not really in the binary tree.
No, forget about the heap sort now. Just this is a general rule with heaps. Forget now. I'm not sorting anything. Forget about this. Okay, just the idea. Do you understand the idea so far? That what is a remove max? It's a remove the root and continue the down heap. But you don't stop after the first down heap. You need to continue till everything. Is this clear? This is very important, guys. Most of the questions is similar to this idea here. Yes, Rab.
This implemented in Downheap itself or in the remove?
Inside, if you look at the algorithm, inside the remove max, it's going to remove the root and then call down heap. function.
Keeps calling it if it's at the bottom.
Exactly, it's a recursive thing. So all of this process is called remove max. Because whenever you remove the max, you need to keep it as a max heap. You cannot just remove max and go home. Okay? So what's going to happen? Yes, Riley.
The way that it knows that it's at the bottom is it just checks and sees that the node is trying to call down heap on, is it a leap?
Yes, exactly.
Okay, got it.
Yes. Now, the next step, I'm doing heap insort. This one here, you're not going to touch it when you're removing the max. So each time you remove the max, you're not going to touch this anymore. How can you do that from a program perspective? Just, for example, do the index -1 as if like you eliminated this, but you didn't remove it from the thing. So this is clear. So now we continued this. Okay, I'm done. What would be my next step? I'm still sorting. So I want to remove max again. I'm going to remove the 20 and put it where? Guys, for people. You had your hand raised at the end.
Put it where the 3 is.
You put where the 3 is. So if I do this, 20. Okay. What should you do next? You want to continue?
Downheap.
Down heap. So you're going to go which way? 19 or 14? 19, and then you continue. So let's see what's going to happen. We continue, restructure. That's the 3, and then I continue again. It's going to be swapped by what? 15. And now it's going to be swapped by the 10. Again, I don't touch this. So now if I tell you in the exam or wherever, give me the sorted numbers so far and the unsorted numbers. What are the sorted numbers? 20 and 22. What are the unsorted numbers? Everything else. So if I put this in an array, so I put 19 here, correct? And then 15, 14, 10, 13, 8, 11. Then I have 2, 3, 5, 4, 1, 7, 20, 22. If I tell you which part of this array is sorted, this, okay? This is sorted, this is unsorted. That's called heap sort in place. You're not using something else. If you have a normal heap sort, you're going to have what? The same array and a different array here that has what? 20 and 22, and this is -2 cells. That's a heap sort, not in place. Yes, right.
If you were to do this with mini heap, you would be sorting from greatest to smallest.
Very good. So this is another very important question. If I'm telling you, I need you to sort the numbers ascending order. You need to start with what? A max heap or a min heap? Ascending order, max heap. Why? Because you're going to always put the maximum at the end. So you need to build the max heap first to be able to sort them ascending order. This is very important. We're going to see one of the tutorials have this question. So very good. We're going to cover it in the tutorial. Yes.
In both cases, whether you're ascending or descending, you're putting it at the back of the array.
Yes, all the time. Why? Because that's the easiest way. We swap it at the end, and then it organizes itself.
You wouldn't want to put it. It's not a array, right?
It's not just best array. It's not a complete binary tree anymore. We're following the structure of a complete binary tree. Okay, so let's move now. Finish this and then go to the tutorial. Okay, so here you can continue it at home if you want to practice, and then we're going to go to the tutorial. I think I have it opened here.
Sorry, it becomes a mini.
Okay, guys. So let's try to solve this together. So this is, again, from a previous midterm. So what are we asked here? In place heap sort algorithm. After the first phase of this algorithm, build heap, the array is as follows. Okay, so in place heap sort or heap sort, we have two phases. The first one is we want to build the heap first, and then we want to sort it. So there, they did the build heap for you, and I have this. This is already built. Is this a max heap or a min heap? Who can tell me? Raise your hand. Yes? Look at it. Look at this one. Is this a min heap or a max heap? These are the indexes and these are the values. If I want to draw this in a tree, how would you draw it? 12 would be at the root, correct? If I'm drawing this, guys, like this, it's going to be 12, 11, and then 9. So that means it's a max heap because the root is the maximum, correct? Very good. Now show the state of the array A after the first two remove max. So this is what we said. When we do a remove max, do we only remove the root? No. What do we do? Down heap. Okay, so let's do it together. So I have this 12, 11, 9, then I have 8. We have 5, and then we have 7. Is this correct? 12, 11, okay. So now I removed the max, so I removed the 12. So what's going to be here? So I have now 7, 11, 9, 8, 5, and what do I have here? 12. Do I write it? No, I need to do the down heap. Is this a max heap? No. So I'm going to switch it with we're going to switch it with this. So I'm going to end up with having 11 and 7. Is this a max heap? Still no, I have an 8 here. So this is 8, this is 7. Is this a max heap? Yes. So now I can actually write it here. So I have 11, 8, 9, 7, 5, 12. Okay, who wants to do the next remove max? Someone who still didn't get it fully. If you got it, that's very good. Ahmed.
I had a question. I might have misheard, but how does he know that was going to be a max heap and not a min heap?
Because look at this. This is 12, 11, 9, 8, 5, 7. So if you're building it, what would be the root? 12. And usually the maximum is the
in this floor.
yes.
Still a question. If I remove the max, do I really need to write it like as a leaf?
Do you need to what if you remove? Do you need to add it? Yes, because we said this is a what? This is a in place heap sort. If it's in place, you need to swap it with the last element. If you're just removing without in place, no, you're going to remove it and put it on the side. Okay? So this is another important question. If you read the word in place, you're going to swap it and keep it. If you don't have in place, you're going to swap it. Yeah, you're going to remove it and throw it away. Okay? Feed it to someone. Whatever you want to do with it. Just don't write it. Who wants to do the second remove max? Fida.
We will swap 11 with 5.
So in the beginning, you're doing a remove max. So I'm going to swipe this with this. So let's write the new one. So I have 5, 8, 9, 7, and then I have what here? 11 and 12. But why didn't you swipe it with the last element, which is 12?
We don't have to touch it.
Very good, because this now you don't touch it. It's the sorted part. You're sorting. This is the sorted part. You don't touch it. Very good. So you're going now, all of these two, you don't touch them. So what do you do next, Fida? You need to transform this into a max heap. So
we swap 5 with 9.
okay, so 5 with 9. So that's 5, that's 9. Do you continue and swap it with the 12? No, we don't touch this. Then what would be the max heap in the array? 5. The whole array, how do you read it?
5, 8, 9, 7, 11, 12.
Okay, if you look at this now, this is the sorted one. Is this sorted ascending order? Yes. Yes.
Swap the 9 and the 5.
The 9 and the 5, it was already 5 and 9, and I swapped them. So look, So if you look here, I switched from 11, I swapped with the 5, correct? So now what do I have here? I have 5 and I have 11.
Then in the next one.
And the next one, what did I do? Oh yeah, exactly. Okay. So 9 and 5. Okay, very good.
That's 5 at the top.
Yeah.
Okay, yeah, my bad.
Okay. It's clear? Good? Yes, Ant.
When we do this heap sort algorithm in place, we're like messing up, we're reversing the type of the heap, right? Because when we have like
At the end,
max heap, it becomes a min heap.
yes.
Okay, yeah. So like,
Sorting it. Exactly. So all of this, by the way, is the solution is here, right? Not in this one, but on the bright space, you'll find the solution. Okay. So now what do I have? So let's go to the second one. Now sort this array again in place in an increasing order using heap sort algorithm. You must show the state of this array after each down heap operation. So that's what I meant. Be careful. The down heap operation is the full thing, not just one swap. Since the first phase must be the bottom up heap construction, please add lines separating the down heap operations and the first phase from the other down. So what do we mean by this one? Here, guys, we already told you this one is already built for you. So this is already built, so you can just start sorting. In this case here, we're saying no, this is the heap is not built for you. So first, build it using what? Which method? Bottom-up heap construction. When you build it, then you start the heap sort. Who wants to build it first, and then we move? So how do I build it? First, let me draw it for you. So this is 21, this is 15, 8, 17, 9, 14. Okay, who wants to build the heap first? James. Yes, so we're going to build it in the array, but first I will help you putting it in the array. But first you need to build the heap. What would the first question you're going to ask yourself?
The first question is min heap or max heap?
Very good. Do you see, guys? Don't skip steps. I told you build the heap, but you don't know. Are you going to build a min heap or a max heap? Who has the answer? Yes. Why a max heap? Was what? Exactly, because we saw this word here increasing. So we know we're going to sort it increasing. That means I need a max heap to sort it in the increasing way. So the first step is done. I decided to do a max heap. So, okay, so how do we do it?
First take the container is already sorted. So it seems like it's already sorted. It's not sorted into max, so we would put the top nodes, we should put it as is, or going into the second and sort it.
Yeah. So because it's a bottom-up heap construction, so we're going to start from which nodes?
And start from the bottoms.
Exactly. So you're going to treat this as a mini heap. So that means I'm going to put this here. So that's 14, and then this is 8, correct? Then you're going to take which second part? This one. Is this a max heap? No. So I'm going to switch. This is 15. This is 17. Okay, I'm good. Now I'll take it all. Is the max heap? Yes, the 21 is on top. That's good. So the first part is good. That means the first thing I did here, guys, I switched the 8 and the 14. Correct? So I'm going to write it here. My first down heap is done. Now I did the second one here. So I'm going to write it here. Correct? That's another one. For the third one, did I do any down heap? No. So what is my status? Is 21, 17, 14, 15, 9, and 8. Correct? Okay, so that's what we mean by put a add line separated. So we're going to say, okay, here so far, this is the bottom up heap construction. Now I'm going to start with the heap sort. So, okay, so what do I have here? I have this 21, 17, 14, 15, and then I'll have the 9 here and 8. Okay, who wants to do the heap sort? Start with the first one. Yes.
21.
Okay, so I switched the 21 and the 8. So technically, what's going to happen here, I have here 21, and then I have here 8. Do I write it?
No.
Do I write it here?
No.
Do I write it?
Oh, no,
I need to do the full down heap. Why? Because each down heap operation, this is not down heap yet. Okay, so what do you do?
so the
Okay.
first thing you would move the 17 to 8.
Very good. So I have here 17, and then I have here what, guys? 8. Is this max heap?
Then move the 15 to 8.
Do I write it? No. That's 15 here, and then that's my 8. Now, is this the max heap? But I still have 21 here and 14. Do I switch them?
No.
No, because this is the, I don't touch it, this is in place heap. Now, what do? I write it here. How do you write it? 17, 15, 14, 8, 9, 21. And then you put what in the exam? You put this like this. That means this is the sorted part. And then I'm going to do one more, and then you can continue it at home. The solution is there, and try to figure it out by yourself. If it's still not clicking, you can go to the TA. Still not clicking, you can come to me. Okay? Yes, Raf.
It's not index 0.
Here, because we're starting by 1, so we just said index 0 is nothing. It doesn't have any meaning. Yes.
Is the biggest.
No, okay, good question. Now, here we're saying we're looking at this before we do everything, right? We're saying, okay, the max, the root is what is the maximum number. Can I say this is a max heap? Who thinks yes? Raise your hand. Who think yes? Yes, 2 people. 3. Only 3 people. Who thinks no? You can't say that. 5, 6, 7 people. The rest, not sure. Okay. If you think no, why? Why it's no? Who had his hand raised here? Zach.
It's not a max heap because it's not sorted like with the parents being larger than the children.
Very good. We don't want to use the word sorted to not confuse with the heap sort, but technically focus about this. It's not just the root need to be the maximum. Each parent need to be what? Greater than its children. So in this case here, in this case here, in this case here, look at this one, okay? I want to erase, I don't know. Okay, so look at this one. We have 21, we have 15, we have 8, 17, 9, 14. The 21 is the maximum, but is 8 greater than 14? Okay. Is 15 greater than 17? No. So the definition of a max heap that the parent need to be greater than its children. All the nodes need to be like that, not just the root. Yes, Joel.
The question doesn't specify it. Do we assume it's a max heap or min heap to our own preference? Like imagine this question, it doesn't tell us to organize it as a max or min.
How did we discover that it's a max heap? Based on what? Your friend here, what did he say? We want to sort it increasing way. If I'm going to sort it increasing way, I need it to be a max heap. Okay? So in the exam, so you don't waste your time and just try the min heap first, it didn't work, then you try the max heap again. No, just think about it a bit. Know that it's increasing, that means it's a max heap.
Depending how the question's formatted.
Exactly. You had your raise, okay, good. Okay, so what is the next thing here? So who wants to do another sorting just very quickly so we lost lots of time? Okay, so I'm going to skip it because no one wants to participate. So you can do it at home. And then we're going to move to the maps. Okay, guys. For the new ADT. So we're going to cover this today and then on Thursday, because this is part of your take-home quiz. The A2 is going to cover binary search tree. After the reading week, we're going to cover AVL tree, and then all of these are going to come in the midterm. These are complicated now. They are simple, but I mean now you need to differentiate. What is a complete binary tree? What is a binary search tree? What's an AVL tree? Different things. So, what are maps? What did we cover before? We said we're using the complete binary tree and the heaps and everything to actually explain the priority queue. Why did we even start explaining the priority queue? What we were trying? Were we just bored? Or there was a reason we chose priority queue? Why did we choose priority? What did we cover? Why did we suggest it? Yes.
We're talking about like data that has like a weight to it. For our example, was the doctor's or the emergency room.
Very good. So technically, we're trying to solve a problem. What was the problem? Did you forget the whole startup scenario and everything? We said we have an actual problem, and we deduced that, okay, to be able to solve this problem, I'm going to choose a priority queue. What was the problem? I want to be able to store and remove things based on their priority. Now, can I use, let's say now I want to hire Taha again, differently right away without startup, without anything. I want to tell him that I want you to build me a like the assignment things where I store the grades of the students, for example. I'll be able to. Can you use the priority queue? If I want you to store the students' information, I want a system that stores student information. Like you're an actual business. We're not analyzing things. So think about it and answer me. Tell me practically we can. No.
I don't think it's the best way.
Why it's not the best way?
Because like the previous problem, the priority was we had to access items like based on the priority, but here there's no priority. Like
very good. So imagine, yes.
Have the names in alphabetical order, that could be used the letters as a key to keep everyone organized in that area.
Okay, what if I don't want to access them by alphabetical order? What if I just want to go and check? So that's why I told Taha, not practically. Practically, you can do whatever you want. We're saying from actual problem solving. If I'm storing the student numbers or the student or all your student information, so imagine you come to me and I want to check your file. So do I have to go alphabetically till I reach you? No. So that means I need now a better ADT that will suits my new problem, which is be able to access the elements in an efficient way, but any element. Why this is useful? In case I want to search. So I want to search. In the priority queue, we said it's going to be very good because we're not even searching. The priority number is going to always be on the root. I'm just going to remove it. So that's why it was very efficient for me. But now in this case, if I'm using a heap, a complete binary tree, so let's forget about the priority queue. Now I want to use an actual complete binary tree. Would I guarantee the same efficiency? No. Why? Because the complete binary tree only guarantees, or sorry, the heap, which is based on the complete binary tree, only guarantees that on the root, I have the min or the max. Yes.
What defeat the purpose of this?
Would what?
What I'm a collection of key value entries, so that means you have.
I still have key and value because why?
Name and grade.
Why I need this? Because if I know your student number, I want to go right away and access your file. I don't want to search. So that's my next question. I would say, what if the common thing between the maps ADT and a priority queue? That's the first common thing, that both of them will have a pair of key and value, not just the value. And that usually is practical because all your information as students are linked to one key, your student number. If I don't link it to this key, what will happen? Who can tell me? What if we have two students with the same first name and the same last name also? So we need to have a unique key. That's the idea or the main difference or another difference between the priority queue and this. So the first difference is that what? We can access any element, not by priority. The second one is that it needs to be unique. You cannot have two same student ID, okay? So first thing is the main operation of this ADT is searching, inserting, and deleting. And then multiple entry with the same keys are not allowed because of what we mentioned now. Because the whole idea for me is I don't want to have duplicate. Applications can be what, guys? Address book or a student record database. Imagine, again, you're designing a phone book and then you're allowing keys to be duplicate. Do you know anyone who has the same exact phone number like the other one? No, it's not practical.
Exactly.
So this is the same exact wording, same exact idea, different wording. Now, the other things that I want to mention is that maps are also known as associative arrays. So if you see it online, the word associative arrays, we are referring to maps. Now, there is something that almost the same exact ADT, but it allows duplicate keys called what? Dictionary. So there's another ADT called dictionary. This one allows the same keys, but it's used for something different than the student address. They have different application for this. Now, again, each ADT, what do we need to define for it? Operations and errors. So these are the operations we need to be able to get, put something in it, remove, and all of this. Now, the put is very important for you to understand what is the put here. You're going to give a key and an element. If this key exists, what will happen? You're going to return the old value and replace it. If the key doesn't exist, you're going to return null. So let's take an example here. So if I do this operation is empty and I have an empty map, it's going to return me true, Boolean. Now, if I put 5 and A, 5 is the key, A is my element. It will put 5A, it will return me null, the put. Now, if I put another one, I want to put 7B. What is the key here? 7 is the key, which is, you need to think about like the index, okay? And then B is my data. Now, again, it returns null. I do it again. I do it again. Now, if I put 2E, look here. So that's 2, this key exists already. It will return C for me, that's the old value, and it will replace it by the new value E, okay? Then get, what's going to happen if I go to 7? It doesn't delete it. It just give me the value of the key 7. The remove will actually delete it. So these are two different ones, remove and get. Okay. Now, actual applications can be a university information system. We said your key would be the student number, and then the value can be your student record. Who can give me another example? I'm going to, doesn't seem there is lots of energy, so we're going to skip it. Domain name system, it's like the website is the key, www.uottawa.ca, that's your key. What is your value of this? What's the actual value? IP address, of course. So this is also another example of the idea of maps. Have you ever seen two same websites? No, because they are based on the map ADT. Now, social media, Instagram, can you have the same exact username like someone else? No. What would be the value of this key? All your information on your Instagram account. You got the idea at this point. Now, if I want to have a sorted map, not just a normal map, so additionally to these operations, I need to have more operations also. If I have a sorted map, that means if I get the first one, it's going to be what? the first index, right? Like I'm able to get the first entry. Let's say I'm organizing my keys from ascending order. So if I do first entry, I'm guaranteed I will have the lowest key at the first index. Okay, so we're just adding two more methods here. Then there's something called submap. That means I can just say I want all the student number between the student ID 20 and the student ID 25. It's going to return me everything between these two numbers. Okay, so that's the idea. This will only work if it's sorted, because imagine it's not sorted and I'm asking the method to return me this submap. Now let's go to implementing the maps. How can we do it? Of course, using unordered sequence, we covered it. And then if I want to also implement, I can use the ordered sequence. These, we know that there is a problem with them. What is, I don't have to repeat myself, what is the problem usually when using lists and sequences? The same exact problem when we wanted to implement the priority queue. What was the problem? Sorry? Complexity, which is what? Linear, right? It's a list, it's linear. So that's why we need to find something better. In the case of the priority queue, we went to the binary tree. We want to do something similar. We want to go to maybe the binary tree. It will not work with the normal complete binary tree, so we're going to do something called search trees. We're going to cover binary search tree, AVL tree, and then 2-4 trees. But we're not going to cover the red-black tree. It's in the book if you're interested in this. The 2-4 tree is not binary, but the binary search tree and AVL tree are binary. And then we're going to learn something else based on the map to solve the map called hashing, hash tables, if you've heard of it. This is also good for the implementing maps. Now, if I want to implement sorted maps, can I use an unordered sequence? Of course, no. And I can't use the hash table, but I can use the other two. We're going to leave this for next time. Let's just do a very, very quick. You know what? Just go home.